would like to acknowledge the tremendous effort of the board members, Azza Al-Akkad, Tawfiq Ayyub, of course, the chair, Medhad Al-Zazi, Nabila Badawi, Sahar Lashin, Sylvia Mansour, Esra Nawar, Adil Salam, and Alfred Shinoda. And also, I'm grateful and thankful to the selection made by the awards committee, Drs. Mahmoud Bayar, Hisham Al-Saifi, and Ibrahim Ramzi. Thank you so much. It's an honor indeed. So I wanted to tell you my story tonight in about maybe 30, 40 minutes. I grew up in Alexandria. Alexandria is a very special town. It is one of the most beautiful cities in the world. And I think a lot of you have traveled all over the world. And there's something unique about Alexandria. As you can see from these pictures, you see that it is endowed with incredible shoreline. It has a lot of beautiful architecture that goes back to the basis of the history of Alexandria as a city where the East has met the West. So you can see from that we have a special affection. And I did grow up in one of the essential parts of Alexandria that's called Bahari. If you Alexandria, you know what Bahari is. So this is an area close to the harbor, and I see somebody from Alexandria. And this area is unique because it is one of the ancient parts of Alexandria, and also it is the accessibility to the outside world. All of the ships will come to that part of the city, so it is kind of a rough area. It used to be quite rough, but of course changes have been made. So in this area, you know that there's the Kai Bay Citadel. It was built in, I believe, 1470. So it was built at the time of the Mamelukes. And it is one of the most important fortifications in the Mediterranean area for several hundred years against invasions of different countries to Egypt. So I used to play over there. And in particular, it is set at the bifurcation between what we call the eastern shore, which is Mina Sharia, if you remember, and the open sea. So it was a big challenge for us to actually try to swim behind the citadel in the open sea. And I did it a couple of times and I survived. I would never do that. So this is where I started, and as I went into college, I started to kind of read a lot of books, and one of the books that I read was about scientists, different scientists. So I was given an assignment to write about history of science, and I was asked to make a report. So I made a report about a great scientist at that time, Isaac Newton. So this was my first, as I tell you how I got motivated. And the way I got motivated is that I stuck in my head that Sir Isaac Newton was born in 1642. He was a genius. So one day he went to the kitchen and he used to have an egg every morning. And at that time, the pocket clock was invented maybe like 50 years before that, so it was very expensive. And he was a rich man. And he wanted to use the clock to time the egg, like today we time the egg for 3 minutes, 5 minutes, so he timed it. And then his maid, he had a maid because he was rich, she walked in and she tapped him, holding the egg in his hand, and then the clock was actually the boiling pot. So I was young and I just said, okay, this is really a weird guy. Why would he do that? Now, what made him motivate him to do that? What makes his head kind of go into this direction? And I realized that actually a lot of scientists are motivated by things other than immediate gratification of money or fame or whatever, because there's something unique about physics. And as I just realized when I got to college with all these wonderful colleagues, I realized that there is something very special about physics because it explains the world. And it is the truth. So we have no choice. There's no opinions. You just have to have the proof and the truth. And it turned out to be that in the world that we know today, there's only 350 years since Newton actually made his contributions. And if you think about it, in Egypt, we count things not by the year, not by the 10 years, not by the 100, but we count things by the thousands of years. So if you think about it, in 350 years, everything that we enjoy today happened, and humanity started 150,000 years ago, as we know it. So you think, like, this is really, truly amazing. Like, how can science kind of make this kind of revolution in a very short time? So 350 years is only about 10 generations. So I said, okay, so how does it work exactly? So it turned out to be that in 300 years, you can divide it into 200 years of what we call the era of mechanics. Everything moves and forces and everything like that. And then the last 100 years is the era of atoms. So the era of atoms was a big revolution in Europe around the 20s and 30s, where actually people started to see the atoms and how they work, and now we have all of this nanoscience and nanotechnology based on that. And then I said to myself, is there something that the Egyptians actually have contributed to? And I found that indeed, in the last 100 years, we had a very great Egyptian physicist, and maybe some of you know him. His name is Ali Mustafa Musharrafa, and he was born in 1898, so that's about 100 years or so. And he was a contemporary of Einstein and all of the great Oppenheimer, all of the people who made the new discoveries in quantum mechanics. So he was well ahead of his time. Unfortunately, he died young at the age of maybe 52 or 55. So he was very, very bright individual. He has a lot of contributions. His student, Samira Musa, she was born in 1917. So that tells you how advanced Egyptian women were at that time. So this is kind of coming from maybe 100 years of contact after Muhammad Ali and Rifat Bahtawi. They went to Europe and they brought in the knowledge. So we had already established maybe a parallel interaction with the developments in Europe and the rest of the world, because these were very special scientists. And as we came here, we all came to America, so now we are third or fourth generation. So coming back, we actually found out that many Egyptians are indeed very, very outstanding. So you can see here, these are people that you recognize, and the three of them were recipients of the same award that I'm humbly getting today. So you can see here, Dr. Farouk Al-Baz. He is a leader of remote sensing, and he is the one who actually established a landing site on the moon for Apollo. So this is the first time for Apollo mission to be established under his guidance. Of course, Professor El-Sayed, Mustafa El-Sayed, he was a member of the organization here for many years, and he was a mentor for me. He's now 84 years old. God bless him. He's at Georgia Tech, still very active, very productive, and he received a very prestigious award, the National Medal of Science. So this is for very, very few people who can achieve that. And then his student, or he mentored, of course, Dr. Ahmed Zuwaid, all of us know him. He passed away, and he was at Caltech for quite a while, and was a member of the organization and received the same award. And he's a Nobel Prize laureate, and he's the father of femtochemistry. So I think the story is that we're all connected, as you can see, like several generations that all relate to the modern history of Egypt in the last 250 years or so, as all of these happens. And I believe that the new generation is just even going to achieve more. So I'm going to tell you a little bit about what I'm doing in my research. I like to work on extreme stuff. So you have some kids, they like extreme sports. So my sport is to look at extreme materials. And extreme materials are those used, pushed to the limit. So materials that are used in nuclear reactors, in aerospace applications, in jet engines, under extreme cold, extreme corrosion, whatever makes them uncomfortable. So we can push the materials to the limit, because usually when something is pushed to the limit, you discover new things happening. So I have a laboratory here in Engineering 6, so I hope some of you can visit us. And it is based on both computations at the nanoscale, so you can see atoms here. We do computer simulations, and then we also have experimentation that I'll tell you about. I also have a YouTube channel. If you would like to kind of subscribe, that would be great. I have like 350 subscribers and 50,000 people look at it. But the idea here is that I would like to disseminate the concepts of mechanical design to the rest of the world. And this is a way to communicate with the rest of the world in an easy way. And as Yahya mentioned, part of our job really is to produce people who contribute to the leadership of education in the world. So there's been 41 years, almost 2,000 engineers that have graduated from my classes. These are filling everywhere in the industry and academia, 120 master's degrees, 40 PhD students, 30 postdocs and staff, and out of those came 16 professors. So one of my earlier students, former students, I graduated from the University of Wisconsin, and I had Jake Blanchard. He was a young student in the 80s, and now he is the executive associate dean of the same university I graduated from. So this is something that we give back. I have a department chair, Hanshin Wang is the chair of the Mechanical Engineering Department at Northwestern University, and I have also the pleasure of having a very prestigious student, Andra Kanaza, former student. Now he looks a little bit older than me, but it's okay. So Andra is a very well-known theoretician, Purdue, and these are examples. The last is Jafar Al-Awadi. He is an associate tenured professor at Johns Hopkins. So this is great. And then these are the faces of various professors around the world that graduated from our university. So I'm kind of grateful to be able to meet these people and have them contribute to the society of education. So now I'm going to tell you a little bit about the materials extreme environment. So the extreme environment that we look at are environments related to the operation of jet engines, supersonic aircraft, fusion reactors, nuclear reactors, laser systems, submarines, the core of a nuclear reactor, and also materials used in space. So all of these materials, they are under extreme conditions of heat or radiation or cold conditions, and they need to be developed. They don't exist, they need to be developed. So I'll tell you a little bit about materials for space, and then the applications in energy. So for space, if you think about it, that we live on an Earth here, and if you go just a little bit like 5,000 kilometers, there's a shield around the Earth called the Van Allen belt, and my friends who are plasma physicists, you know that. And that shield has a magnetic field, and that magnetic field traps all of the radiation coming from the sun. So if it wasn't for this shield, we would be fried here on Earth. So something very unique. And once you go beyond this Van Allen belt, which is the little orange here, then you get into less and less pull from the Earth's orbit. So what happens is that we send rockets outside to get out of what is called low Earth orbit. So once you go out that, then the gravitational pull is lower, and then you can actually put satellites. So you can see now there's 3 circles. And the one circle at top is called GPS. All of us have the GPS in our pockets, right? So you have everything. This is a navigation system, worldwide navigation system. The GPS is a US-based system, has 33 satellites, but covering the Earth. So we can communicate with each other. Then what happened is that other nations found out that if you can control communications, you can control many aspects of life, including war and peace, everything. So other nations started to put their own systems. So you can see that the Russians put the GLONASS system right below, and the Chinese are building their own system of satellites. So there's a lot of competition on how to get there. And if you go farther out to about 35,000 kilometers, then you get into an orbit that's called geostationary. So if you put a satellite there, it moves exactly with the rotation of the Earth. So it's kind of seeing the same spot. So how do we get there? Well, we get there using rockets. So the stronger the rocket, the more you can get up there, and then beyond, of course, you can go to Mars or you can go to the moon. So the first rockets that were built were based on a very famous guy's name is von Braun. So I don't know if you know von Braun. He was a German scientist in the Second World War that was actually kidnapped or taken by the Allies and brought to the United States, and somehow he converted, became the leader of this technology, and he developed the only rockets that actually work. These are the Saturn rockets. So this one here is show you that the Saturn rockets are the strongest, and they are the ones who took us to the moon, and they can take us to very high orbits where we need to go to mission. So if you can look at this video, it shows you that the rocket, when it's launched, you get extreme heat, and you can see these little falling pieces. This is ice because it starts at a very cold climate, and then all of a sudden you kind of shoot it up. So the material that is surrounding here doesn't know what's going on. It's just really an extreme environment. So, and now the lives of people who are actually on the payload or on the rocket depends on how they survive. So to give you a summary, this is kind of all of the rocket systems that have been built. So von Braun was right down here, and then as time goes on, then the Saturns that I showed you here, it's pretty big, like 300 feet long, so it's very big. So these are called heavy rockets. So they just kind of take huge loads, and NASA right now is building something even stronger than Saturn. This is called the Space Launch System. It hasn't been finished yet, but it's 384 feet high. So it's a gigantic rocket. So what happened is that a young guy from South Africa, his name is Elon Musk, he came here and said, well, this is kind of ridiculous, I can do better. So what he did is he built a bunch of rockets here. I'm going to tell you about in a company in California called SpaceX. And his idea was completely different. These rockets are expendable, so you spend like billions of dollars, and then you shoot it once and it's gone. So that's a waste of resources. So his idea is to build rockets that can actually go up and deliver a payload and come back and then be reused. And that's what he did. So taking out of So this is one of his rockets coming back. It's an animation. So it delivers and it comes back to the Earth. And his design is that it has enough guidance to come back. So it's coming back, and it's going to come land right here. And of course, once it lands, you can reuse it again. So that saves a lot of money. And then his payload is right here. So the payload has propulsion system, and all of a sudden, you find this car. So he has a Tesla car. That was his first stunt to deliver. But of course, he has his eye on the future, how to use all of this. So what I'm going to tell you about is that the thrust now, once you get this payload up in one of these orbits, there's very little gravitational pull. Then you don't need really a lot of fuel to push things around, because the big rocket, you have to have chemical fuel, and it's a lot of mass to kind of push it up there. But once you're up there, then you don't need that. And then even if you have chemical fuel, it's not going to last, because you need to kind of keep going. So what happens is that once you get to here, then you need to find some other way. And this other way is called electric propulsion. And that's what I'm doing now. So electric propulsion is to find some kind of, cathode and anode. So it's like electricity. So you have a little bit of gas, and then you have an arc, like a spark. And then the gas gets hot, and then you can get propulsion coming out. So there's different methods. Electrothermal, electromagnetic, can also have magnetic field, or electrostatic, where you have a grid right here, and the grid will pull the ions, and the ions will come out here. So this is what we're working on. And what I wanted to show you now is, if you see the payload, it went up there, and then it needs something to pull it. So what happens is that we develop something called the ion thruster. And the ion thruster is like a can. And the can here has a grid. And if you take a cut, then you have a chamber. You put a bunch of magnets, because the magnets are like a spider web that can catch electrons and the ions. So this is why we have them there. And then you put some grids here. The grids are electrostatic, so they can pull any charge, just like electricity. And then you introduce atoms, and the atoms, they split into an electron and an ion. That's the plasma, electron and ion. So you pull the atom comes in here, it splits, this is an electron, this is a neutral, then they kind of do something, and then you have ions coming in here, and then you have this grid to pull them through. So when these guys come out of the grid, you know what the velocity is? It's like what they can move in 1 second is what your car moves in 1 hour. That's how fast they come out. And that's why you don't need a big mass. Like in the rocket, you need a lot of mass, you need a lot of chemistry, right, to pull that. But this is different. This is, you need a little bit, but then you pull them out at extreme velocity. So what happens is that with that extreme velocity, when you pull them out, I don't know if I showed you the end of this is something that you need to see. This end here. So you can see now, this is the neutralization, and then becomes the atoms, and that is this glow that comes out of here is pushing down the satellite. And this is what you see in the movies. So in the movies, you see this kind of glow coming out. That is basically very high velocity ions coming out of this can. But what happens to this can is that you have grit, and the grit gets hammered. So you can imagine if you have something like 60 kilometers per second hitting that surface. So what's going to happen to that? You're going to have a lot of holes, you're going to have a lot of fractures. Actually, the material, like you see this here, it kind of disappears after a while, actually. So if you're up in space, like you have a satellite that it costs like $1 billion to launch a satellite, and you have a little piece like that that goes wrong, then you are up shit. correct. So you have no choice. So satellite's going to go down, and then you can't correct it. There's nothing you can do about it. So what we do is we try to find materials that can solve these problems. Of course, we cannot defeat physics because things have to break, but we can make it longer, prolong the lifetime of the material. Just like prolonging the lifetime through good medicine, we prolong it through material science. So here's another example is how materials work in the Space Shuttle Columbia. We all remember that there were two major problems or disasters that happened in the Space Shuttle. The Challenger was in 1986 and Columbia was in 2003. And the reason that these happened is due to materials problems. So this is the Space Shuttle Columbia, and it's coming down to Earth now. So it comes down to Earth. It has something called aeroheating, so it heats a lot. And when it heats, it makes plasma. So the plasma is surrounding the space shuttle coming down. So what you do, you put like materials that can resist that heat. And you can see under the belly here is where the materials. So these are the materials that have to resist. Unfortunately, these materials cannot be very reliable sometimes. And what happens, you can see now it's breaking up. This is the real one, and it's breaking up. 7 astronauts lost their life. So we need to have reliable materials. Now all of us, we travel on planes, and we put our life on the plane. And the plane is propelled by a jet engine. So the jet engine here is something like a fan. It takes cold air. You burn kerosene right here, and you get hot air that wants to expand, and then you get thrust. So the blades here are under extreme conditions of heat, and heat flux and erosion and deflection. And you need to be careful that they can last and not affect the plane operation. So what we do, we use computers to help us before we do the testing. We take a blade, break it down into little pieces in the computer, we put all the channels in it, and then we do what we call simulation. Simulation is like make-believe. So you just put it on a computer, and then kind of pretend what happens to the flow. So you have flow here, does it kind of pull the heat enough, or doesn't pull it enough? Can you actually redesign these holes, and can you figure out what's wrong? If I have that, this is kind of the stresses here. Red means kind of danger, so you kind of try to do that. And we do iterations, many, many iterations. Once we find the right size, the right dimensions, then we can go and recommend this needs to be manufactured, and you reduce the cost this way because you don't have trial and error. And what I wanted to show you is what happens to materials when you do computer simulation. So computer simulation, we have atoms here. This is a laser impact on this material. And then you can see the wave, and then it breaks up into pieces. So in the computer, you put equations for maybe 10 million of these atoms. They're all connected together. So you have to do the simulation to do that. And if you, as I said, these particles that hit the surface, we try to understand what we do. So if you have like a particle coming in here, it creates like a collision cascade, like just billiard balls. It makes a hole in the material, and it comes off. So we understand how it works, and then we can go back and then make it more resistant. Now I'm going to talk about the next subject, which is material for energy. And material for energy, this is how I started. I think this would be an interesting part of the talk, because the future depends on supply of energy that is clean. And here we work on fusion energy. Fusion energy is the plasma that I showed you, but at much hotter conditions. So we make it very, very energetic. And so we have here plasma in the center, and for us to make it really high energy, we have to put magnets. So we have magnets around here to confine it, and then we have a reaction. So you have two isotopes of hydrogen, deuterium and tritium. They collide, and they become two different ones, helium and neutron, and they release a lot of energy. This is the idea of fusion. And once you have this, then you have heat exchanger, and you have electricity. So this is the idea behind fusion energy. And fusion energy is there is a project in the tokamak. So I'll let you watch this and I explain.
Atoms will heat and control the plasma or the fuel in the reaction process. The plasma is an ionized gas made up of the hydrogen isotopes deuterium and tritium, and will eventually
so these little bubbles here are supposed to be atoms, so they're very, very tiny, like ions. And we have here an accelerator to inject very high energetic ions, because you have to light up the match. It's basically you have to light up the match, and you have to heat it up. And also you use like microwaves, so you're going to heat it up. Then you have it here confined, and as these are going to collide, you see that they have collisions, and each collision here produces fusion energy. The white part is like energy coming out.
They transfer energy to the plasma, thereby heating it and driving
Yeah,
charge.
so you can see it is heated. The music, of course, is nice. And now you have fusion reaction propagating, and all of a sudden you achieve conditions that propagate by themselves. You don't need to heat it anymore. You use the match to light it up, and then it's done. Now, this is not, what you saw is an animation, so it just shows you the idea. But actually, the project is already ongoing. It's at a place called Cadarache, France, and it is a collaboration between 35 countries, and the US is one of these countries. So it's being built in Cadarache to have this idea, and it is halfway through, so it is 50% done already. And the project is going to cost $22 billion. It seems like a very large number, but this is not the largest, because the space station costed $150 billion. So it is a very important project, and we're expecting to have achieved fusion energy in the year 2035. It got pushed back because it's very difficult technology. But as you can see, many countries are actually working on it. I have to also say that in this room here we have some of the world experts. Professor Abdu is world expert on the thermonuclear systems around the plasma to convert energy. We also have Marie Chokri, who's worked all of his life on plasma physics, because this plasma is like a gas. If you squeeze it too hard, then it kind of wiggles and it kind of loses its position. It's called instability, and Marie has been working on many applications of that. So now I'm going to show you that once you have this, if you go inside the tokamak, it's like a donut, big donut, like this. Then you have the plasma is at 150 million degrees. That's how hot it is. But the magnets are confining it, so we don't want it to go to the walls, because nothing is going to stop it. Right? You have 150 million degrees. That's a lot of energy for your body. So we don't want to stop. So, but even though we have very powerful magnets, and we also have here one of the world experts in magnet design, Dr. Sam Gourel at GA. They deliver some of these big magnets to ITER. Then inside we have to use armor, just like the knights in the Middle Ages, so you have to have this armor. And this armor is made of this material called tungsten, which is the highest melting point on Earth, 3,500 degrees. But still, this tungsten doesn't last very long. So I take it to my lab, and then we test it. So we try to simulate what the conditions are. So we have two test facilities at UCLA. One facility is in collaboration with Professor Bortz at Van Gogh. So this facility, you can see the plasma here. We put materials on one end, and we accelerate the plasma to hit the material, strike it, and then we take it out, we look under the microscope, we see what happened, compare it to the computer simulations, so that we can see how to design materials better. And that's kind of one of the facilities that we have here at UCLA to test materials. So this facility here, inside is vacuum, complete vacuum. So it is like our space. So it's very, very high vacuum conditions. And we have another facility in my lab, and this facility is to address the question of heat. So as we showed you that there's tremendous heat that comes in, and this heat is coming in, like I have a plasma gun coming from, you can see here, like we produce conditions that are extreme, and we put the materials, we cool it, of course, and we control it, and then once we slam it in, it's kind of fun, take it out, see what happens, and then what you can do to change it. So what we do is we microengineer materials. We go down to the basic level. And you can see here that these are materials that we produce, and the microengineering is the surface. So we change the surface to be like pillars coming out of the surface, or to be like foam material. This is tungsten. And the idea here is that if you have ions going through, they get lost inside. So you have a lot of holes that just catch it, like foam to catch it inside. They collide inside, and then they produce no major problems. And this concept is called self-healing materials. So they kind of try to heal themselves. As you use them in space, they extend their life a little bit more, and you keep that satellite a little bit longer in space. So I think this is kind of my story in a nutshell. I know that it's difficult to have a kind of a bigger overview, but I give you an idea about our research. And now I wanted to go into a little bit of philosophy. So what happened is that I joined this organization 40 years ago, and some of the founding members, like Dr. Bayar and Sabri Abdulaziz and others, do you remember that? It seemed like it was yesterday. It wasn't really a long time ago in our lifetimes. And since 40 years, we have seen tremendous changes in the technology and how it affected our lives. So back then, we used to have no significant computations. Now, your little iPhone is much more powerful than the biggest Cray machine that we used to have these days. So I'm going to speculate that in 40 years from now, maybe many of us are not going to be here, but the younger generation will. What's going to happen is that there are so many developments. As I said, we had 350 years since Newton was here, out of many thousands of years, and that made tremendous change. And for those of you who are engineers, we know the law of exponentiation, like it goes exponential. As you learn more, you make other people learn, and then others make learn, and so on. So in the next 40 years, I think is going to be equivalent probably another 400 years from the past. So I would think that there's going to be self-driving vehicles everywhere. Next month, we know that in LA County, they're giving the first licenses for self-driving vehicles. So you can imagine the changes that will take place in the society based on that. People are going to maybe move farther out. Maybe they're going to be greater traffic jams because they don't want to leave their cars. Maybe not. I mean, the challenge is going to be there's going to be the technology, but it's going to create a great dislocation of society if there's not an effort to actually organize what happens. Artificial intelligence is going to be pervasive everywhere. Right now, if you go to Alexa and you tell her the wrong command exactly, she doesn't respond. But because there's a lot of very smart people making artificial intelligence, I think many machines are going to exactly know what you're talking about in the same way that we think. There's going to be extensive robotics and automation everywhere. So every aspect of our life, we're going to see that. We most likely are going to see bionic human systems that are called like part human, part bionic replacements and so forth, extending lifetime. Hopefully cancer cure, because there's a lot of work on that. I also believe that there's going to be clean energy, and the final solution is two, solar and fusion. There's no other alternative. After all is done, if you go to China, you're going to find that it's a beautiful country There's a lot of developments, but you cannot live there. And the reason is the environment. So if we don't solve the environmental problems that come with energy, we're not going to be living. So there's going to be a lot of work on clean energy. And also I think there's going to be the production possibilities is going to move more towards 3D printing. So right now we have some of, this is an example of a fuel injector in the jet engine that I showed you, and it's totally 3D printed from metal. So you can imagine big components that are coming out from your printer. Because of also we're suffering from global warming, I believe that there's going to be a reversal of global warming. And finally, because the population is going to increase and we need faster communication is going to be ultra-speed transport. So with that, I thank you all and for being here, for participating, for your support, and I feel great pride in our heritage as Egyptians and Americans at the same time. I feel that Egypt is blessed as a country because of the rich history. Egypt is not Arab, is not Muslim, is not Christian, is not Pharaoh, is not Roman. Egypt is the product of all of these things that happened over the years. So it's a very special country that we should all feel proud of. So thank you very much.
Thank you, everybody. This concludes our formal program. Please feel free to stay and socialize. Also, our photographer, Sophia, will be here taking photos of friends and family. And thank you very much for joining us tonight.